Hi, welcome to another video in database internal series. So in the last video, I briefed upon why fanout, a low fanout is bad for on-disk storages, but I felt that I could have gone a little more in depth. So in this video, I'm going to be doing exactly that. I want to cover a little bit more about fanouts and explain things with a couple of examples. So let's get started without any delay. So low fanout, like binary search trees for on-disk storage, is it good? Is it bad? Let's discuss on the same. So before going ahead, we need to understand what fanout is. Fanout is nothing but the maximum number of allowed childs per node, and this is of course in the context of trees. Now let's discuss on disk seek time and latency. So low fanout implies more tree levels for the same amount of data, right? If you have a low fanout is nothing but what maximum number of allowed childs per node. So when traversing a tree stored on disk, each level in the tree typically requires accessing a new node. And what this implies is more levels equals to more disk accesses or seeks. So low fanout means more levels, and then more levels implies that you will have to access more number of nodes, and more number of nodes access means more disk access or seeks, right? So let's understand this with an example. So let's assume that we have 1 million entries, and we have a binary tree which has a fan out of 2, and we have a B tree which has a fan out of 100. So what is going to be the tree depth in case of binary tree? It's going to be 20 levels, right? And in case of B tree, it's going to be just 3 levels because the fan out is 100. So you can always argue, right, that you are following pointers in both the approaches. What difference does it make? Well, it of course makes a difference because the number of levels in B trees are significantly lesser, and more levels because it equals to more disk accesses for B trees because it has significantly lesser levels, meaning the disk seeks are reduced significantly, right? So even though you still need to follow pointers in a high fanout tree, the number of pointers followed is much smaller, and what this does is it significantly reduces the number of disk seeks. Okay, so B trees have far fewer levels due to a high fanout value, which naturally means fewer nodes overall, and fewer nodes means what? Fewer disk accesses. Okay, so even when nodes are scattered, right, you can always argue that, because inserts are random and nodes are scattered across the disk blocks, which typically does not happen because the fragmentation bit is taken care of by node splitting and rebalancing in a B tree. But let's assume for the sake of this discussion that your nodes are scattered across a disk. The number of disk accesses needed to traverse a tree is minimal compared to a low fanout tree, right? Okay, so moving on to the next bit, which is how does a high fanout solve locality? And by locality, I'm specifically referring to spatial locality here, which is data should be as close physically as possible, right? So does fewer nodes mean better clustering? Well, let's see. With higher fanout, fewer nodes are required to store the same amount of data. And we'll see data storage efficiency between BSTs and B trees with an example, with a very interesting example. Okay, so since nodes are larger and hold more entries, related data entries, which is just the child nodes, are packed closer within the same or adjacent nodes, right? And one interesting thing is B trees are typically optimized for disk block size. A B tree node is typically 4 kbs, and 4 kb is what? A typical disk page size, right? Now let's see low fanout. What happens? Low fanout leads to scattered data, and nodes contain fewer entries, so more nodes are required to cover the same data set. So data storage efficiency is like very bad when it comes to low fanout trees. Now these nodes are scattered across disk, and accessing related entries may require jumping between widely spaced disk blocks. And if you're jumping between widely spaced disk blocks, in the in the context of hard disk drives, the disk head has to rotate, and the more the amount of rotation, the IOPS gets affected very badly. Now let's discuss about storage efficiency when it comes to BSTs versus B trees with a very interesting example. So consider you have 1000 nodes of a balanced binary search tree. So what it will contain? 1000 keys and 2000 pointers, one for left and one for right child. Okay, so total size per node is going to be 8 bytes for the key, 8 bytes for the left pointer, and 8 bytes for the right pointer. So per node size is 24 bytes. That means for 1000 nodes, the entire size is going to be 24 kilobytes. So assuming that your disk block is storing 4 KB, you will require 6 disk blocks, right? But let's see what happens in B tree. So you have 1000 entries in a B tree. So let's assume that you have a fan out of 1000. So single node can hold up to 1000 entries. What this means is you can have 1000 keys and you can have 1001 child pointers. So let's see the total size. So total key size is going to be 8 KB. Total pointer size is going to be again 8 KB, because 1001 into 8. And the total size per B tree is going to be what? 8000. 8 KB plus 8 KB is 16 KB. Now let's see what is the number of disk blocks required. It's 4. Assuming that your disk block is 4 KB. So you can clearly see that between 6 and 4, the storage efficiency of B trees is way higher compared to BSTs, and also data access is not going to be a pain, because what? It has lesser levels. Less levels equals to less disk access or disk seeks, right? So this is it for this one. I wanted to kind of cover this aspect because I think it's quite fundamental to understanding why B trees are often chosen as the data structure choice for on disk storages. So I hope this was of help, and I'll see you in the next one.